Hi, today we're going to wrap up our study of electron dot structures by talking about the concept of resonance structures. A very formal definition for what resonance structures are is that they are two or more chemically equivalent electron dot structures for the same molecule. So I underlined chemically equivalent here because a lot of people do not initially understand what that means. So let me start by showing you a molecule that we looked at in a previous video, and let's talk about what chemically equivalent is. So if you'll remember, when we were doing formal charge, we looked at two possible structures for carbon dioxide. And the two structures I showed you were these. One with two double bonds. And remember that if you have two double bonds, you're going to have two bonds that are exactly the same length. And then one that had one single and one triple bond. And this is going to have uneven bond lengths with the single bond much longer than the triple bond. Because again, the more bonds you have holding two nuclei together, the shorter the distance between them is going to be. So these two structures are not chemically equivalent. They don't behave the same. And therefore they are not resonance structures. So now let's look at another molecule, ozone. Now if you went through all the math, etc. for ozone, you would end up with the fact that it needs 3 bonds. And so you could draw 2 possible structures. So I often put these structures on the board and I ask people, are these actually the same structure or are they not the same structure? And usually the class is split about 50-50 that yes, it is the same structure. Well, what would happen if you rotated it like this? Now suddenly it kind of looks like it is the same structure, isn't it? I mean, the unshared electrons on the central oxygen look like they're in a different position, but we all know that those unshared electrons are sort of buzzing around anyway, so that might not be a thing. Well, let's think about ozone again. And this time we're going to color one of the oxygens green. Now obviously we can't actually color an oxygen green, but what we can do is we can do what we call isotope labeling. Roughly 99% of oxygen is oxygen 16, but what if you were to put in an oxygen 17 or an oxygen 18 for one of the oxygens at the end? Now you can see, if we rotate it again, there is a difference between these two structures. And so we need to think about what it means to have 2 double bonds and 1 single bond. If indeed the ozone was going to have 1 double bond and 1 single bond, the double bond would be shorter. So generally speaking, oxygen-oxygen single bonds are 1.48 angstroms. Remember, an angstrom is 10 to the minus 10th meters. An oxygen-oxygen double bond is 1.21 angstroms. So that's about 14% shorter. So is this what we see in ozone molecules? Well, no, we actually see oxygen-oxygen bonds that are 1.28 angstroms. And both of the bonds of the molecule are 1.28 angstroms. So you have to ask yourself, is this a single bond? Or is it a double bond? Or is it both? So what happens is one of these pairs of unshared electrons moves to become a double bond. And since the central oxygen can't have 5 pairs of electrons, one of the pairs of electrons in the other double bond goes to the other oxygen and becomes an unshared pair. And this just moves back and forth so quickly that it's essentially 1.5 bonds for each of them. That's what a resonance structure is. These are chemically equivalent structures. And the truth of what ozone is not one of these structures or the other structure. It is both of them. And it's just constantly interconverting back and forth. So what we're going to do is we're going to practice writing resonance structures. And we're going to do this for 2 different molecules. So I'll start with an easy one, the carbonate anion. And we're going to start this the way we've always done our electron dot structures, because you can't really write resonance structures until you come up with a good electron dot structure. Again, we're going to start by finding the total number of valence electrons. Carbon has 4. We have 3 oxygens, each of which have 6, so that's 18. And again, this is an anion with a -2 charge, so that gives us 2 extra electrons, and so therefore we have 24 electrons. Now we need to figure out the number of electrons to give everything a noble gas configuration. Carbon has 8. Each of our 3 oxygens is going to want 8 as well, so that would be 24, which gives us a total of 32 electrons. So how many shared electrons would we have? We'd have 32 minus 24, so 8, and that means we'd have 4 bonds. So now we can start drawing. We're going to put in carbon at the center, and our 3 oxygens around the outside, and we're going to put in bonds. 1, 2, 3, but we need 4 bonds, so one of these is going to have to be a double bond. Now we can distribute our unshared electrons. We started with 24 valence electrons. We've used 8 of them. That means we have 16 left. Now, for each of these oxygens that has 1 bond, those have 2 shared electrons, so they need 6 more to get an octet. 2, 4, 6, 2, 4, 6. And then our double bonded oxygen has 4 shared electrons, so it needs 4 more to get an octet. And just quickly, we have 6 and 6 and 4. That adds up to 16, so we did that right. And then finally, this is an ion. We need to add brackets to it and put a charge on it. And now we have a good electron dot structure for carbonate. Now we are going to draw resonance structures. You always have to ask yourself, does something have resonance structures or not? Now, if you remember, when I was originally drawing this structure, I said we needed 1 double bond, and I put it in a random position. But does that double bond have to go to that particular oxygen that I picked? It doesn't, because you can see it can also go to the oxygen to our left. Notice I've put a double-headed arrow between these structures. That indicates that the electrons can move back and forth between these structures. And then, of course, there's that third oxygen, which could also have a double bond. So this has 3 different resonance structures that the electrons can move between. Finally, we're going to draw resonance structures for the sulfate anion. I love using sulfate as sort of the final structure that we do as we talk about electron dot structures, because it ties together so many of the concepts that we have discussed. So we're going to start out the same way we always do, by finding the number of valence electrons. Sulfur has 6 valence electrons, and then we have 4 oxygens with 6 each, so that's 24. And don't forget that this is an anion with a -2 charge, therefore we have 2 extra electrons. So in total, that gives us 32 electrons. How many electrons do we need to complete our valence shells? Well, sulfur would want an octet, so 8. Each of our 4 oxygens will want an octet, so that's 32, and therefore we need 40 electrons. How many shared electrons should we expect? Well, 40 minus 32 is 8, and so once again we're going to have 4 bonds. So now let's start drawing. Sulfur in the middle, because it's the least electronegative. 1, 2, 3, 4 oxygens. And then bonds, 1, 2, 3, 4. Now we can distribute our unshared electrons. We should have 24 of those. And if you look, each of our oxygens has 1 bond, 2 shared electrons. So each of them will need 6 electrons. And does that make sense? Well, 6 times 4 is 24, so yes. So we're going to have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So there is our structure for sulfate. And one more thing to do before we finish our steps, and that is to add the brackets and our charge. Okay, so here's our structure. And what I want to do is I want to calculate formal charges. So let's start with the oxygens. You'll notice that all of the oxygens have the same electron configuration. That is, they have 6 unshared electrons and 1 shared electron, so that's 7 total electrons. And oxygen normally has 6 valence electrons, so every single one of these single bonded oxygens will have a formal charge of -1. Now let's look at sulfur. Sulfur normally has 6 valence electrons. In this particular case, it has 4 shared electrons, no unshared electrons, and so we have 6 minus 4 is +2. And I want you to think back to the rules of formal charge, which is that non-zero formal charges should be minimized. So you should have as few as possible atoms having a non-zero formal charge. How many atoms do we have that have a non-zero formal charge in this molecule? None. So from a formal charge standpoint, this is a really rotten structure. What can we do to try and fix that? Well, sulfur is in row 3. It can have an expanded octet. So why don't we take one of these pairs of unshared electrons from an oxygen and turn it into a double bond and see what happens. So that's what I've done here. And now let's go and evaluate formal charges. We still have 3 single bonded oxygens. Those will still have a formal charge of -1, but we now have a double bonded oxygen, which has 4 unshared electrons and 2 shared electrons. So that would have 6 minus 6 equals 0. And so let's pop that formal charge in there. And now let's calculate sulfur. Sulfur has 5 shared electrons. A free sulfur would have 6 valence electrons. So the charge on sulfur is 6 minus 5 or +1. Now this definitely looks better than what we had before. We now have one atom that has a formal charge of 0. We still have 4 that aren't 0. So if making one double bond made the situation better, what would happen if we had 2 single bonds? Let's find out. Now let's calculate formal charges for this structure. Again, we have 2 single bonded oxygens, and we've already calculated that the formal charge on those is going to be -1. We have 2 double bonded oxygens, and we've already calculated that the formal charge on a double bonded oxygen will be 0. And then we have to calculate our sulfur. We know that sulfur normally has 6 electrons when it's on its own. It now has 6 shared electrons and no unshared electrons, so that gives it a formal charge of 0. Okay, now we have 3 atoms with formal charges that are 0 and 2 that are non-zero. So what would happen if we made yet another double bond? And so that's what I've done down here. Again, as we look at formal charges, we have 1 single bonded oxygen and 3 double bonded oxygens. We already know the charges on those. We can calculate for sulfur, which now has 7 shared electrons and no unshared electrons, so that would be 6 minus 7 would be -1. So there we go. So again, we have 3 atoms with a formal charge of 0 and 2 that have a -1. Does this make sense? Well, actually it does. We can never really get rid of atoms with non-zero formal charges because the formal charges always add up to the charge on the molecule, and this molecule happens to be an anion with a -2 charge. So the best we can do is having 2 -1 charges. So we have 2 structures that have 3 atoms with a formal charge of 0 and 2 atoms with a formal charge of -1. Is one of those structures preferred to another? So now we go back to our formal charge rules, and what we see is that if you have to have formal charges, ideally you would have the negative charges on the more electronegative atoms and the positive charges on the less electronegative atoms. So which of these elements, sulfur or oxygen, is more electronegative? Oxygen is. We know sulfur is less electronegative, and that's why it ends up in the center of our molecule. So we want to have our -1 charges on oxygen if at all possible, and that tells us that this is our winner. The 4th structure has a -1 charge on sulfur rather than oxygen. So now we're going to take our optimum structure and we're going to write resonance structures for that structure. Remember, resonance structures are chemically equivalent. So if you look at the structure, you see a sulfur surrounded by 4 oxygens, and it's bonded to 2 of those oxygens with double bonds and the remaining 2 with single bonds. So what we need to think of is Is there another way to have two oxygens with double bonds? And people usually come up with this one right away. Is that the only way that we can have two double bonds? No, it's not, because we can also, let's say, do this, and that, and that, and that. There are 6 possible structures. So this idea of resonance looks kind of crazy when you think about all the possible structure, but really what it is showing you the possibilities of where those electrons could be as they move throughout the structure. Resonance is a way of explaining why instead of having a bunch of single and a bunch of double bonds, we actually have a whole bunch of bonds with equal bond length. I hope this was helpful, and I look forward to seeing you again soon.